All right, so this week is mostly going to be about networking and networking protocols, as well as IP addressing, etc. So again, as I was mentioning to the guys before we started here today, you guys should have most of this down, as you should have taken the internet networking course here at Fort Hays, or maybe a transfer credit that gave you the equivalent and gave you the basics of what network operations is all about, the basics of the different protocols, and how data is encapsulated and transported across that network. I may move through this fairly fast, as you have 3 sections this week. There'll be 3 separate recordings, one for each section that you'll be covering. If I don't get all to them today, you guys should have those released. So with network communications, networks vary in size. There's a wide range of different simple networks, from as simple as 2 computers to networks connecting millions of devices. So whether it's your home network or your business network, they all follow, for the most part, the same basic principles and the same basic rules. A peer-to-peer network is generally just like in a small business or home. Computers may function as both servers and clients in that network. They just call that peer-to-peer. In other words, this is something that doesn't necessarily go out to the internet. Obviously, these days, everything pretty much connects out to the internet. So small home networks, and these are just what they call various different networks that you'll be quizzed on, I'm assuming. So your small home networks are just a few computers that are going to talk to each other, as well as the internet. And then you have your SOHOs, which is your small office, home office. Those are going to allow you to connect to a corporate network or access some kind of centralized shared resources. In a home environment, this may be like if you have a NAS, network attached storage, or maybe you have a server or something like that at your house. That would help classify it closer to a SOHO. If you're using VPNs and stuff like that, that's a little bit different connecting here. Now, if you used a remote office that had a firewall with a VPN connection back to a corporate, that would be more classified as a small office, home office. Your medium to large networks, this is typically your corporations and schools can have lots of these, many locations, hundreds, thousands of interconnected hosts. And then, of course, the worldwide network. This is basically the internet, which is just a network of networks that connects a bunch of people together. So client-server communications, everything connected to a network participates directly in the network communication. Those are classified as hosts. Hosts are basically your end devices, endpoints, nodes. This could be your laptops, desktops, all your IoT devices, etc. Those would be considered hosts on the network. Servers are typically reserved for computers that have specialized software that enables services that can help be either single purpose, they could provide one like web pages or something like that, or multi-purpose, providing email, file transfers, LDAP, authentication type stuff. Those are all going to be server based. And you could obviously have a laptop that acts as a server on your network too. These don't have to be a physical, rack mount server that you have. So a file server is going to just store corporate files and user files in a central location. Again, this should be a fairly good review. So you have your file client, web client, email client, and then you have the various servers out here on the network. Again, these can be condensed down. So this could be physically one server on the network, or it could be 3 individual servers, depending on how it's split up. In today's world, this gets even more complicated, as this could be one physical host, but have a bunch of virtual machines on it as well, right? So virtual machines have really changed a lot of what you see on a network. So a typical session, this is going to be something where, students are encouraged to use laptops and networks and stuff. I won't cover too much in here. But the idea is that when you make a search on a network, that's going to be transmitted wirelessly from whatever device. It's transmitted back to binary, then sent through a radio wave, and then converted to electrical signals, and then go out to the ISP network, returns all that, and vice versa back. So one of the things we'll talk about, like when gaming, you guys are probably all familiar with this. When you have gaming consoles that play games against one another, you're using that ISP and a router or cable modem, whatever you're having at your facility, in order to connect to your home network and get internet access. And the big thing with, gaming, while they're talking about here at a basic level, but you obviously want to make sure this is extremely low latency, right? So any good gamer that's playing more than the casual game will know that latency is very important. And of course, in medical consultations, especially with telehealth and everything going on in the world this year, telehealth is huge. And this is going to be where they can send x-rays and they have to send massive amounts of data that's stored at one particular location. My girlfriend, as a matter of fact, is studying to be a naturopathic doctor. And so I'm encouraging her to work hard in telemedicine, as you can do that from any place. And so even in remote Western Kansas, Hays, Kansas out here, she could do telehealth anywhere. So very important in order to get that data across there. We even have programs within the informatics department that specifically focuses on health information systems, and where you take your networking knowledge and you are certifying or working yourself towards working in the medical industry. So you actually start to learn the medical terminologies and all that kind of stuff in order to see what's going on there. All right, so this is going to just have a practice utility is all this is. You guys will see this inside of your modules when you get to working with that. But the idea is that you'll have an understanding of how these networks operate. So a cybersecurity analyst, you have to understand how that traffic is going across the network, right? So we not only have to be network engineers, which is typically, you know, the networking track that we have even within the informatics department, but we also have to be one step above that in order to have all of that knowledge and then be able to dissect that information and really see what's going on. And you get a little bit of this in the networking curriculum, a little bit of troubleshooting. The CCNA curriculum has grown tremendously compared to back even when I took it. As a matter of fact, we had to wait for a lot of CCMP stuff in order to do that kind of troubleshooting. Now that's all been put back into the CCNA program. So CCNA is significantly more involved than it was even 20 years ago. Oh my goodness, it was 20 years ago. All right. So when tracing a path and going through here, this is how you can figure out your hop count. They won't talk about that necessarily here, but hop count's going to be a huge thing, as well as doing trace routes, and you guys will be able to do that, in which case that's what you're going to do here in the lab. So one of the labs that you guys will have this week is tracing a route and understanding how you can trace things on a network. Now you may have a couple hops, you may have multiple hops, but if you guys have ever worked on a help desk or internet troubleshooting or something like that, which are great jobs while you guys are trying to become cybersecurity analysts, strongly encourage it. Especially if you're out here in the Hays area. We have a couple ISPs in town that work fantastic in helping you get those skills. And they love our students because they're really well skilled and trained. But that lets you, one of the first things you'll do is do a trace route, right? And this trace route will give you back feedback as to how many hops there are, and each hop is determined by a different device that your traffic has to pass through. So, and these are all at the routing level. So for example, if I did a trace route on my machine to go out to Google, you're going to see my laptop's IP, then you're going to see my router's IP, then you're going to see my ISP's level router, and then the routes that go through the internet to get me all the way out to Google. And what's nice about that is, particularly with some ISPs, you may have multiple routes to get to a certain destination. So for example, the ISP here in town, Nextech, has multiple uplinks, and they have multiple 10 gig uplinks. Depending on where they want to route that traffic is to what link they want to send that out. So for example, if I'm sitting at my home here in Hays and I want to send traffic over to Fort Hays State University directly, so I'm either accessing Blackboard or I am accessing materials there on Fort Hays' campus, there's a direct pipeline between Nextech and Fort Hays' campus. So instead of sending it clear out to the internet, going up to a tier 1 ISP and then turn around and coming all the way back down to Fort Hays, they've actually installed a link directly. And why would they do that? Well, it eliminates the upload traffic that's going on their outbound link. Extremely smart on their part, right? So they don't have to pay for even larger links. Now, again, today they have lots of 10 gig links, but that wasn't always that way when I worked there. They only had like 1 gig links, and they may have had smaller links from Candrin and such. So by having that direct link, they really limited the amount of traffic that was going there, as most of the people in Hays were using it to go to Blackboard, right? Or some other Fort Hays campus when they were at home. So troubleshooting that communication would be great. If I notice there's a huge amount of latency on there, then I need to go in and find out why is it going out this route and not across that direct link. And trace route utility that you guys do in that lab will help you establish that. Some communication protocols. We talked about protocols in the past in your internet networking courses, but there's different protocols that are used for different things. And a lot of that has to do with latency and the time it takes to get that packet across the network. Some of those are going to be governed by different rules, and so there's standards on all of this. However, just because a protocol's here doesn't mean it can't be tweaked, and you can use modified protocols. The problem is when you modify those, you are adjusting things that everything on the network has to adjust. So what am I talking about? Well, if we're using things like IPv4, right, or even IPv6, with IPv4, it has a set format, it has a set size, the timing, how it's delivered, whether it's TCP, which is going to be, your transmission control protocol, basically has a sliding window, or if it's UDP, which means you may get it, you may not, because there's no checks and balances on UDP. So those are the common ones that you guys will all deal with. HTTP, obviously, for all your websites. Today, almost everything is HTTPS. So you just have a secure transfer going across there. And so if we look at a message structure here, you're going to have something like this. So this guy's going to send a message. He's going to encapsulate it in an IPv4 header, forwards this out to a router. He understands the IPv4. He doesn't necessarily care about the data. All he cares about is what the IP address coming in and how he can route to it. Looks up his routing table, sends it across, and gets it over to the server in this case. These guys all determine which connections are there. So like, for example, here you have a multiple route, right? So that packet could come down here, go up, go down, go over, or it could go straight through here. And how those routes work are all based on what you set for your route priorities. And typically they have a metric or something like that, that allows you to set the lowest cost path. And it depends on different protocols, again, that you can use for routing. So there's a ton of different routing protocols you guys can learn. So these are all sharing just unique ID numbers. They're all talking about different paths basically here. And the idea is that they can determine that a specific path is down and therefore it can't connect to that. And so therefore it wouldn't allow it to go out this A connection and go on up. So TCPIP is going to be one of the main ones you guys are going to use. It's the most common one that's out there today. There's several different ways to use TCP/IP. You have your open protocol standard, which is out here. Anybody can use that. And then you also have a standards-based protocol suite that goes down here. So this is most of what you guys will see on the TCP/IP protocols. For example, at the application layer, you may see DNS and POP3 and FTP and your web services. In between on your transport layer, this is where we were seeing TCP and UDP. Again, connection-oriented versus connectionless. And people always ask, if you didn't catch it in internet networking, why would I use UDP? And typically UDP is when you don't necessarily care if the packets are out of order or whatever's coming through. You're just going to blast that traffic out. So if you guys have ever had, internet-based TV from maybe your Nextech or Eagle here local in Hayes, not so much Eagle because they're on the cable side, but if you ever had anything from Nextech where you're actually getting IPTV, IPTV is typically sent over UDP, which means they're going to send you a packet. If you don't get that packet or if it comes out of order, that's where you just notice a blip on the screen, right? And usually it can reassemble and put some things together, but it has no idea what that packet is going across. What's nice about UDP is it's extremely fast because you don't have to have that connection, that three-way handshake that you typically have with TCP. On your internet layer, you're going to have things like IPv4 and maybe some NAT going on. And then at the very high level, you're going to have your routing protocols. And this is what we were talking about earlier as to path selection. So you could have just a static routing, or you could use variable protocols. For example, OSPF and BGP are extremely common, particularly BGP at an ISP level. You typically won't see this at your corporate network or something like that unless you're connecting multiple networks together. Definitely aren't going to see BGP at your house. Network access layer, this is where you're going to have your address resolution, ARP, and your Ethernet or your wireless connections that are going to come through there. So I won't go too much in here as we got further in there, but when we talk about DNS, this is your domain name. This is what's going to translate your name to your IP address. DHCP, V4, V6, those are how you can get automatic IP addressing so that you don't have to manually configure everything. And then you also have Slack, which is available in IPv6, which is a stateless address auto configuration. On the email side, you have some 3 common protocols, SMTP, POP3, and IMAP. These 2 are almost dead as they're not commonly used anymore. IMAP is by far the better way to go. The difference between them all, most of you probably have never dealt with POP. POP was where the email is retrieved to the mail server, and then you have a client that actually downloads it off the server. That means if the client dies, for example, the laptop dies, the hard drive dies, etc., you lose all your email because it's already been downloaded off the server, right? The server's not storing that email for you. In an IMAP situation, you have a server that stores the mail. You just have clients that are able to access that email from everywhere. And obviously, IMAP was a huge explosion and way better today because I can have my email accessible from my phone as well as my laptop, maybe my desktop, my tablet, etc., and they all have the same email. Where in the POP3 days, if I downloaded it on my phone, which wasn't very common because you didn't have smartphones then, but when you did have that ability, if you downloaded it on one computer and then went and got your email on another computer, those 2 didn't have the same emails, right? There was no copies left on the server. You had already downloaded them. So IMAP is a pretty standard protocol that's out there today. File transfer, we have FTP, SFTP, and TFTP. Again, in today's world, FTP used to be a huge file transfer server, a protocol that the people used all the time. Today, everything's a little more secure. That's why you're all in cybersecurity, right? So SFTP basically uses the same FTP protocol. It just establishes an SSH connection over that, which gives it a much higher level of security because everything that you transfer is encrypted. TFTP rather, is just a connectionless, best effort, unrecognized file delivery. So the only place you tend to see TFTP now is probably in your Cisco networks. A lot of times you will use this to load up Cisco iOS images and transfer those across that kind of thing. It's a very simple FTP server. However, again, it's there with best effort. So if you drop a packet or something happens along the way, you got to start the file transfer all over again. Web services, as we talked about, HTTP, HTTPS, you guys should be familiar with that. REST is a very common protocol now. This is typically a web service that has an application programming interface or an API and sends HTTP requests to create web applications. So a lot of web applications today use the REST protocol in order to interact with that web server and create a dynamic web application. So if you have a flat static website, you're probably going to see HTTP, maybe HTTPS. If you have any kind of logins or anything like that on your website, that should all be HTTPS. Otherwise, REST is typically used for web apps. We talked about TCP and UDP as to whether one's connectionless and one's connection-oriented. IPv4 and IPv6, again, hopefully you guys are familiar with this. This should be a review. IPv4 is using a 32-bit address. IPv6 is 128-bit. They've been talking about, going full bore with IPv6 since I was back in college. It hasn't hit the main street yet. There's obviously things that use IPv6, and we had some real need for IPv6. But as long as we have NAT out here, typically NAT will cover most networks. And so there's a few benefits with IPv6, but for the most part, as long as you can understand NAT and really use NAT, which is going to translate your private IP address space over to a public IP address, then you don't have to have so many public IPs. Everybody was thinking, all these IoT devices and everything, they all have to have public IPs and they can get through there. Well, that's great, but at the moment you give them public IPs, that's where you cybersecurity analysts step in, right? You're going to realize that there's no security. There's no way to block that. Now, you can put a firewall and some things in front of it, but as long as you're natting that traffic and you're having to open up ports, which is a little complicated, but it's a whole layer of security that you can put on your networks, especially during your home networks. Messaging, we talked about ICMP. This is typically your ping traffic that goes between there. That way you can find out whether a host or a source is there, errors in packet delivery, etc. Routing protocols, we covered those pretty good as well. On your network access layer, this is your ARP. So if you guys remember ARP from Internet Networking 1, this is what's going to allow you to translate between your IPv4 address and your hardware MAC address. So a lot of times you'll send out an ARP ping. A switch is usually what your computer's connected to these days. And so that switch is going to translate whatever your IP address is on that port, convert it to a MAC address, then send that MAC address, and it goes down through the different protocol layers. Typically we use Ethernet today. This is for all your wired and signaling at the access layer. So your 10, 100, 1000, 10,000 that you have today in terms of transfer speed. And then your wireless LAN. This is going to be all your wireless networks that you guys are familiar with now. This is basically all the wireless signaling that can go between 2.4 gigahertz and 5 gigahertz radio frequencies. So again, you'll have a little structure here that'll take you through message formatting and how that's all encapsulated. So, you know, they always use the analogy of taking a letter. You're going to write the letter, put it inside an envelope. That's your encapsulation. And then de-encapsulation just is the reverse order of that. So when the recipient gets the email or the mail, they open the envelope, which unencapsulates it. Then they get to read the letter that's inside. On a network, it happens the same way. So you have this message formatting that's going through there, and this is your typical header. So in an IP protocol header, you're going to have your version for these couple bytes, the traffic class, and a flow label if these are set, otherwise they're empty. And then you have a payload length, which whatever your data is, this is going to give that length there. A header and then a hop limit, and you can set these on a per IP basis. You'll have your source address and your destination address. And, you know, we all use devices today without even knowing this level of detail, right? But the thing is I can manipulate that packet, and I can do all sorts of things like that to fool your network into doing things that you wouldn't normally get back. For example, I can get on your local network and I can poison your switch and do what's called a man-in-the-middle attack, so where you're sending all your traffic through me and then out to the internet, which basically is injecting a route inside of there. And by doing that, I can then see all the traffic that's going across the network. Even if you're using HTTPS and all of that in between, I end up jumping in between there. And by being in between, I can actually act as the SSL certificate inside. Now, HTTPS is a whole complicated, and we won't get into man-in-the-middle attacks. But you can actually house the certificate, and you guys would never know the difference, especially back in the day when we dealt with man-in-the-middle attacks on wireless more than anything. You could poison a wireless network really fast. And if I was sitting at a hotel, I could collect all the data from all the different people that were connected to that access point. On the network side, this is, you know, just showing different videos that will show you how to encode this. You guys will see this in the curriculum and the content, so I won't stay too long on that. The flow control is just going to tell you how that information is sent and at what speed it can be delivered. Response timeouts, as well as access methods. You know, how are you connecting to this NIC? Is it wireless? Is it wired, etc.? In terms of unicast, multicast, and broadcast, so a unicast is usually a one-to-one delivery where you're sending messages specifically to one client. A multicast means that one host is sending that message out to everybody on the network. So this multicast, typically this is going to be used for, again, like TV delivery. IPTV is all done over multicast, which means I'm broadcasting on this address. You can subscribe to that as a client, or you cannot subscribe to that, but it's coming to you no matter what. On the broadcast side, this is typically used by your switches, etc. This is for making sure that you can go find IP addressing information, typically is what that's for. It's a limited section. You're not sending it out and flooding it out to everybody. You just have a select few that you're going to send that out to. All right, so benefits of using a layered model. Again, you guys should all be familiar with the OSI model, which is going to deal with physical, data link, network, transport, session, presentation, and application, working from the bottom up, and how that correlates to your TCP/IP protocol, and then further on to the TCP IP model and how those correlate in between. So the OSI model, you guys should be familiar with this. This is definitely going to be on the exams. Note how this maps over to the the TCP model. So note that application in the TCP model is both application, presentation, and session over here in the OSI model. Transports match up, internet and network is on the same level, and then network access is going to be your data link and physical layer. Let's see. So your physical is just going to be, and I'm going to start from the bottom up because that's how the traffic goes out. So this is going to be however your electrical, mechanical, or, however you're sending this physically across. So whether it's electrical impulses or maybe you're sending radio waves, etc., that's how that's going through there. This is going to say how you want those data frames to be on that particular media. Is going to be the data link. Your network is going to exchange pieces of data over the network. This is your IP and that kind of such there. And then you set your transports as to what protocol you want to use in order to segment and transfer and then reassemble that data on the far side. Your session is going to be a service to your presentation layer that's up above that organizes the dialogue and how that data is going to be exchanged. On the presentation layer, you're going to transfer that data between the application layer devices that are up above, and then of course your protocols are used for process communications. On the TCP, you're going to see, or the internet model as it's often referred to, so that's one thing to keep in mind for reference. On the network access, you're going to see your hardware devices and media that make up your network, and then determine the best path going through that network is your internet layer. Again, this corresponds to your network layer on the OSI model. And then on your transport layer, you're going to have communications that go across different devices. And then, of course, at the application, you're going to be seeing the encoding and the actual dialogue. All right. So for data encapsulation, this is how it's going to segment. So we can't just send one blast big data all the way across the network, right? We have to chop that up into smaller units, and that's typically referred to as segmentation. And those packet sizes can vary in what that data size is going to be. So if you're on a typical network, you may have a MTU or maximum transmission unit of 1500. And that 1500 is where you're going to chop that packet up in bytes. It's usually a little less than that, so like 1492, just to stay below that 1500 threshold. Now you could use things called jumbo frames, which allow you to send up to 9,000 byte packets going through there, which sounds great. You can send a lot of data very quickly. However, everything on the network has to speak that same language. So if you adjust an MTU up to 9,000, you have to do it for everything on the network. Otherwise, you're going to start having traffic issues. So the benefits of segmenting those messages is you can send a large data stream. It can be reassembled. It doesn't have to tie up that communication link. Obviously, this isn't as with the bigger links and everything that we have going out to the internet now, that multiplexing is going to be the big thing where you can send multiple packets all at the same time. You're not going to chew up the link. And this used to be an issue way back in the day with some older networks that were not Ethernet based. So sequencing, again, you can send these packages out. They mark these as label 1, 2, 3, and they may arrive in a completely different order, but you can then reassemble them on your side to make sure that they're put back together in the right order. Protocol data units, or a PDU. This is just a form of data that takes away that layer as part of the protocol stack. So at each stage, it's going to reflect its new function. Whether you're talking about a datagram on a UDP packet or an IP packet is typically referred to as an IP datagram. So protocol data units, that's what you're going to see here. And this is just, again, working through the stack. You're going to see your frame header, your network header, transport, the data, and then the frame trailer. And that's all split back out to ones and zeros. 3 addresses, what they're talking about here is your main 3 addresses that deal with on a network. So you're going to deal with the physical, which is going to be your ones and zeros, on-offs. At the data link layer, this is your physical address and or MAC address. Network layer, this is your network host address or your IP address, and then your transport layer is part of that as well for using TCP if you want to use TCP across there. So encapsulation, again, I'm not going to go through these. You guys will see these inside the curriculum. Your de-encapsulation process, when it reverses it, and then you guys are going to get to see Wireshark. So Wireshark is a very big tool. I think you guys have used a lot of that in internetworking class, and this allows you to see exactly what's going across the wire when you send and receive packets from a computer. So definitely be familiar with Wireshark. You should become very familiar with Wireshark and how to use its tools. There's entire courses just for Wireshark, and I think there's a Wireshark Academy. I've seen, the basic levels of Wireshark, and I've seen the people that created Wireshark and actually demonstrate those at conferences. They can do a lot of cool things with Wireshark. It's extremely powerful in the right hands, and it really helps you troubleshoot and see what's going on the network. It's known as a packet sniffer, and there's several other packet sniffers out there. You could use the very basic level one on, like, say, a Linux system called TCP dump, which is just going to dump all those packets out, and then you have to use something to read that. That typically goes into what's called a PCAP file, or packet capture file. And then things like Wireshark can read that. What's nice about Wireshark is it'll give you a visual, and you can actually follow a stream and do some things like that, which you'll do inside the homework, or inside the lab rather. So to summarize what we got through here today on network protocols, networks come in all sizes. We know that larger businesses may connect to tier 2 ISPs through a point of presence. Tier 3 ISPs connect to homes and businesses to the internet. Your network protocols may specify features of network communication, such as your message encoding, message formatting, encapsulation, and how it's being delivered. Remember that those common protocols are going to be like DNS, DHCP, POP3, HTTPS. The OSI model has 7 layers. TCP model has 4 layers. This is a key. I guarantee this will be a question somewhere. Data being broken into smaller pieces and sent over the network is called segmentation. When we multiplex, this just basically means that we're sending multiple data communications or conversations happening at the same time on the network. And PDUs are going to be your protocol data unit. Don't confuse that with a power distribution unit. And let's see here. De-encapsulation is just a process of when you receive that packet and tear it back down. So that covers network protocols. That's the end of this